silence. And this is a difficult task to make an introduction of his whole career. It will take me 1 hour. So I'm trying to summarize the most important points about, or what I consider the most important points about his career. He got his bachelor from Berkeley University and his PhD from Wisconsin University. Later, he moved to England, I think.
Arizona first.
Arizona, later England. He was director of CTIO during 8 years. Later, he was director of Space Telescope Science Institute at Baltimore. And during those days, was during 5 years, I think, 1993 to 1998. He has the idea to dedicate the telescope to something that nobody thought before. I mean, in fact, the HST never have a scientific case for cosmology, but he has the wisdom to think that the telescope should try to go to one of the fundamental questions in cosmology, and was the PI of the Hubble Deep Field that now is very famous field, and started a really new branch in astronomy. But I would like to say, especially for those young astronomers, that now you are so used to logging to the internet and to access all databases with very nice quality data, that 15 years ago things were not like that. There were very, very few legacy projects. Just IUE has a database that was available. IRAS did a all-sky survey. But we didn't have this idea about research. Research was focused on small groups that they have proprietary data and they didn't want to share with other people. But Bob has the wins, though, to think, no, we really need legacy projects that are going to be useful for the whole community, not only for me or for my friends. And he released the data as soon as the data was ready. There were not any proprietary right on the Hubble Deep Field. As an anecdote, I remember during a storm blizzard at Baltimore, sharing my room with Mark Dickinson, that was struggling with the data reduction, because he told me that they should release the data next week. And there were no excuse, even a storm blizzard, to not release data. Well, later, right now, Bob is the president of International Astronomical Union. He's visiting us, and well, I should mention that he's been working on analysis of spectral lines on different objects like nebula, accretion disks, active galaxies, and nova, and now he's going to talk about nova. He will be here just today, so he will be in Ramon's office, so if anybody want to talk with him, he will be ready to meet the people here. Okay, thank you.
Thank you, Arturo. What has really interested me for the past 30 years are nebulae and these objects. You see Nova Scorpius. 2007. Novae have fascinated people for years for the obvious reason. You look out, you see 6,000 naked eye stars. They all have the same brightness year after year. Every once in a while, something pops up, and then it disappears. So, natural to think, what's different about those objects that suddenly appear? They're either associated with the birth of stars or the death of stars. And so for centuries, people have thought that. And it's the obvious thing to think. Wrong. Both ideas. Novae have nothing to do with either the birth or the death of stars. Very interesting. And we've only come to realize that in the last half century. Novae, of course, were studied in Eastern societies ever since the time of the Roman Empire. Probably even before, but that's when the historical records begin. They are all in Eastern societies. In the West, we were under the influence of Aristotle. He said the sky was unchanging and perfect. Therefore, novae did not exist. Amazing, because you can see these things. And there's only Clark and Stevenson have looked at all the records, and they find 2 records until the time of the telescope, right, 1600, of new objects, guest stars, in Western societies. Simon and Garfunkel were right. You know the song, The Boxer? A man hears what he wants to hear and disregards the rest. And so we disregarded this. But in the East, they saw these things and they recorded them. Japanese, Koreans, Chinese, particularly the Chinese, who have written these histories of dynasties. And I have taken a special interest in them and visited Taipei and inside the mountain there where you go and see the records, particularly of the Qing and the Ming dynasties, where they have records of all of these. So I want to break the talk into 3 parts. The history of novae, then the middle part, the current paradigm, what we now understand about novae, which, by the way, is largely correct. And then the last part is some research that I've been doing, some of it with Alessandro here and other collaborators that you see there at the lower right, Massimo Della Valle and Elena Mason. And some modifications we believe are necessary for the nova paradigm, which has been very successful for half a century, ever since it was first postulated by Bob Kraft, based on some observations, and I'll explain that. It's like the sun. We understand a great deal about the sun, basically. But several decades ago, there was this problem with neutrinos that required some modification. And so you have all this data on the sun. You have a lot of data on novae. Basically, the models of the sun were correct, but it needed some tweaking and some new understanding of particle physics. Well, the same thing's true of novae, where we have lots of data. We have a successful paradigm, but I believe that it needs one important change, and that's really the whole point of this talk. So let's start with history, because it's kind of fun. And I recommend this book to you. It's 40 years old, maybe, Historical Supernovae by Clark and Stevenson. And they went back into all these records and tried to find evidence for novae. By the way, Mira, the variable star, reaches 3rd magnitude. Even in Eastern cultures, there's almost no mention of Mira. And so the feeling is that if a nova reached 3rd magnitude or more, it would be seen. And if it didn't reach 3rd magnitude, it probably was missed. They show good records for 75 guest stars, as they're called. We used to call them nova, but now we know that most of them, in fact, were supernovae. But that distinction didn't exist. In any event, guest stars. The Chinese divided up the sky. Got to stay here within the boxing ring. So they divided up the sky into 280 asterisms. Well, we call them constellations now. We've got 88. They had 280, and they represented everything important in Chinese life. You know, the royal family, the palace, the garden, other important things. Astrology and astrometry began with the Chinese because the appearance of a guest star was considered to be an omen that meant something. And since the sky was divided up into fairly small sectors, here was the asterism Wei, W-E-I, This represented the royal family, and this actually is the bottom of Scorpius. They call it the dragon, and that's the tail. We call it the tail of the scorpion. They call it the tail of the dragon. So you can see it's much smaller than the constellation Scorpius. So if a guest star appeared in here, it meant something. So the astrology, it meant something for that individual. On the other hand, if it was here, didn't refer to that individual. It referred to the next thing. And so the position of guest stars was very important. And so the construction of measuring devices actually began in the Roman Empire with the Chinese, because it was important to them that they determine exactly what asterism the guest star appeared in. And they had court astrologers that interpreted. And that's sort of like the Bible, where you have Joseph, right, who's people who interpreted dreams. So here's several records that come from this book about various guest stars, which we now believe were supernovae. Okay, one in the Han Dynasty, again, time of the Roman Empire. Then several events that were later in the Qin Dynasty, and then the Song Dynasty, which actually was the supernova of 1006. You can see that the interpretations here were the following. I don't know if you can read it. It's a little small. The governor of the metropolitan region punished and eliminated the middle officials. So-and-so attacked and killed someone else. The general of chariots and cavalry and several thousand people were killed. Bad news. There was an eclipse here. So-and-so, king of Quangling, accused of plotting rebellion, committed suicide. Okay, that was in AD 65. Then AD 369, this was a supernova. The interpretation, when a guest star guards 2A, is assassination of the emperor by his subjects. In the 6th month, so-and-so was dethroned the emperor. So all these things were bad omens. However, with time, they improved. So here by 1006, you have actually a disagreement between two astrologers. And for this particular supernova, brings prosperity to the state over which it appears. That's good. On the other hand, his or her colleague, over the state it appears, it presages military action, death, countrywide famine, so the population would seek refuge. So slowly, the predictions became better. And I've often wondered, why is this? And I only found out recently that the dynastic histories in China are not written by the dynasties themselves. They're written by the succeeding dynasty. You know this famous expression, history is written by the victors, not the losers, obviously. So the reason that most of the predictions were bad is because each one of these is written by a scribe that refers to the previous dynasty, and these were usually used as a justification why they defeated and overtook that dynasty. Interesting. In any event, so the beginnings of astrology and astrometry. We do it better now. But if you're a director, you have to be careful. Anytime a nova appears, maybe bad news. Modern interest in novae occurred with the famous nova S Andromeda. It appeared in 1885. Now, of course, this is before extragalactic objects were known. Everything belonged in the galaxy. All those fuzzy spots up there were gaseous nebulae. They were not galaxies. So this object, and this is an actual photograph. Now, it doesn't look like it, but it is a very early photograph. And, of course, I downloaded this from a scan of a Nature article here that you can see in 1885. And now we know it's a supernova, but, of course, that distinction didn't exist then either. And it occurred right there. It caused a sensation, made front-page news. New York Times, Europe. It was discovered in Germany by German astronomer Hartley. And it became famous because Laplace had suggested that stars form out of the collapse of gas clouds. So here in Andromeda, you have the Andromeda Nebula, thought to be a gas cloud. New star appears, confirmation of Laplace's theory. So quite quite a spectacle. It caused some important people to go into astronomy. E.B. Frost, who succeeded George Ellery Hale as director of Yerkes, entered astronomy because of this object. He was a senior at Dartmouth College. You had to write a thesis. He wasn't sure. He was interested in something non-science. This came about, and he thought, wow, this is interesting, and so he became an astronomer because of this. There are other examples of that. This one object which existed for some months. In any event, the other interesting thing is this, we now know, supernova, achieved fifth magnitude, which is roughly the same brightness as novae in our galaxy. So it also was a confirmation to people that, whatever this is, it has a distance that is the same as other objects in our galaxy. And so the curious thing is now, it was Ritchie's realization that this is really something that's different. Now we call it a supernova that should be ignored. It caused everyone to believe for decades that this fuzzy object was in fact in our own galaxy. So interesting coincidence. It wasn't until Baden's wiki defined supernovae, and Ritchie found other novae in M31, which were all at 16th magnitude. He had 6 of them. He realized, hey, there's something weird about this thing. So he discarded it, and that's what caused Heber Curtis, who was a colleague of Ritchie, to realize, I can get the distance to this thing, and it turned out to be, almost 1 million parsecs. So interesting history here. Very central in the Curtis-Shapley debates and the determination of the extragalactic distance scale. Okay, so interesting history. Characteristics of novae. There are about 30 of them that go off in our galaxy every year. We don't see most of them. Sun's in the way, extinction, happen not to be looking. That'll change, of course, with SDSS and LSST. You can see here a plot of the number of novae that are discovered in the past century in 5-year intervals. A century ago, 1 nova was discovered per year on average. Recently, that's divide this by 5, so that's about 6, 7 novae now. Amateurs are looking much more. In fact, Bill Liller, former colleague of mine down in Chile, he himself has probably found 30 or 40 of them. He must hold the record. In spite of the fact that in Viña del Mar, he's got the marine layer coming in all the time. But Bill, he's a fanatico, fortunately for us. Light curves. They decay very fast and very smooth, or very slow and very bumpy. And the parameter that's usually ascribed to them is the T3, the time it takes in days to decline 3 magnitudes from maximum. And you can see this was only 9 days to drop 3 magnitudes. It's a very fast novae. Here it took, 2.5 months, very slow. It's been a puzzle to explain why there are these bumps. And the current paradigm does not explain those. It's a puzzle why some of them decrease and then reach a maximum again. So I will suggest a solution to that problem, basically. That is the change in the nova paradigm. Interesting, novae-form dust. I happen to be a colleague of Frank Lowe's, who passed away just recently in Arizona for many years. I remember in 1970, his office was down the hall. Frank had developed the infrared bolometer, pointing it at the sky, pointed it at anything that came up, novae. And then Nova FH Serpentis in 1970, I remember him coming and saying, my God, all of a sudden it's blasting out in the infrared. Well, the fact is, historically, a few nova were known to, after a period of weeks, suddenly drop down and decline and then come back up after months to the brightness they would have had if this decline had never happened. And what Lowe and colleagues, and now Bob Gary, many infraredders, of course, measure these things. Here's an example, nova 20 years ago. At the time that it suddenly starts dropping, you can see that it comes up in the infrared. This is the optical here, and you can see that it has an optical spectrum, nothing in the infrared, and as soon as it starts going down at day 83, boom, it comes up in the infrared, and the black body is 800 degrees. So dust forms, and it forms in this object 3 months after the outburst. There are novae for which dust forms 1 week after the outburst, which is really interesting because tremendous explosion, high temperatures. Within 1 week, dust is precipitated. Now, there's some interpretations that this is pre-existing dust that's way away, and so the dust didn't really form. Almost no one believes that anymore. Because of the temperatures, it does have to form closer to the novae, so dust can form very rapid time scale. A few novae are spatially resolved. They look like planetary nebulae. They are not. Here's GK Persei nova from 1901. So this is what it looks like with Hubble 100 years after the outburst. Lots of inhomogeneities. Same thing, recurrent nova T-Pix, 25 years after its most recent outburst. Lots of inhomogeneities. DQ Hercules, 50 years, half century after outburst. And here, Nova Cygni, 1992, taken 1 year after outburst with the Hubble. It looks a little smoother, but probably we just aren't able to spatially resolve them. The surface brightnesses of novae are 4 orders of magnitude less than planetary nebulae, so they are very hard to detect. And usually, because they are expanding, they dissipate. They fade away to nothing before you can detect them. So there are very few examples of resolved novae. But one can do a nebular analysis on them, and some of us have done that in past years. Treat them like planetary nebulae, and the reason their surface brightnesses are so much less is because their masses are 4 orders of magnitude. A planetary has half, a third of solar mass. It is measured that the masses of the ejecta of novae are 10 to the minus 4th, 10 to the minus 5th solar masses. So that's why very low surface brightness is very faint. But when you do study them, their nebular emission, classic nebular analysis, apply cloudy to it or whatever, you get some interesting results. Generally, you find high helium. Generally, you find that they're enriched in helium. So high helium, and also enhanced in the heavy elements. You can see here, compared with solar, this is what Z is. And look, it's 1 to 2 orders of magnitude over the sun. So most of that's carbon, nitrogen, and oxygen. So 2 important results from the nebular analysis. In the ejecta, they're very, very enriched. You're seeing nucleosynthetic products there. So, now to the nova paradigm. The accidental discovery that really is the key to our current understanding of novae. Just push me if I walk outside. Occurred in 1954. Old novae were known to flicker. And so in California, there was a lot of study, photometric study of nova, trying to understand what these objects were, because nothing was known about them, really. Merle Walker, using I think it was 100-inch, the hooker, was looking at the flickering one night in August. 3-color UBV. Here's a chart recording, strip chart recording, the good old days. And you can see here a dip, very symmetrical, that indicated an eclipse. Interesting. So he went to night lunch, came back, eclipsed again. An eclipsing binary having a period of 4.5 hours. That was orders of magnitude less than any other known binary. Short period binary, 2 stars going around each other in 5 hours. Interesting. So everyone dropped what they were doing, started to look at old novae. And within a month, another one, UX Ursa Majoris, was found to eclipse, same period, 4 hours, 54 minutes, I think it was. So, looked like nova systems, circumstantial evidence, had something to do with short period binary. Very interesting. How can you have 2 stars going around each other in 5 hours? Bob Kraft looked for, to eclipse you have to have inclination greater than 80 degrees, so most objects won't eclipse. So he started looking at these things spectroscopically, Wilson and Palomar. And this is in a decade later, 1964, he published the result of a study of 10 old novae and dwarf novae, some of which eclipsed. And he found basically that 7 of the 10 that he studied had evidence for being short period binary. less than a day, 1 hour, 3 hours, 4 hours, 48 hours. So it appeared that the nova phenomenon had something to do with short period binaries. For the few eclipsing systems, one of which is UGEM, BQ-HER eclipses, he found that the eclipses were very deep and with a very short ingress and egress time, meaning that what was being eclipsed was very small and very high surface brightness. What stars are very small, very high surface brightness? There was only one type of star known at that time, white dwarf. So, based on that evidence, Kraft proposed a model. Well, based on that evidence and two theoretical studies that had been done a decade before, people were trying to, after Boden's wiki defined the difference between novae and supernovae, it was realized that there were two types of supernovae. And so the theoreticians were wondering, well, two things. First of all, why do some stars explode? Most stars just sit there stably because of the perfect gas law, right? If you have a temperature fluctuation, energy goes up, but it expands. Adiabatic expansion drives the temperature back down, so there's equilibrium. So it was Leon Mestel who in 52 was wondering about this also, and he realized that a white dwarf could accrete hydrogen material, and if it did, and he didn't do the calculations, that it may explode like a gigantic hydrogen bomb and be observed as a type of supernova. But he didn't do the calculations. He did a conceptual study based on the equation of state that was taken up by Fred Hoyle and Willie Fowler, who wrote this seminal paper on the different types of supernova. And they did the calculations, and they came to the conclusion that there were two ways of getting an explosion in a star. And one was the ignition of degenerate nuclear fuel. The other was endothermic reactions, and they proposed that this is what caused the two types of supernova. And later in this article, they say, we expect that explosion will always take place if explosive nuclear fuels become degenerate. So they were in Pasadena talking with Kraft and Walker, and these ideas came together, and Kraft said, so we've got a white dwarf in all these things. Okay, that was just recently after Chandra had realized that the degenerate equation of state was temperature independent. I'll say more about that. And so Kraft proposed this model that still is the nova paradigm. Okay, so if you talk to any of us who study nova, this is what a nova is. And there's still a lot of truth to this. But I believe there's one important thing here that needs to be changed. And we'll end the talk with that. And it's basically that this is not what causes the accretion. In fact, it goes the other way. But later. So what Kraft proposed was, okay, you got a close binary. It must be so close that, and one star is a white dwarf. So here's a white dwarf. This high surface brightness on it. You've got the secondary star overfilling its Roche lobe. That will cause some material to flow out this way into the gravitational potential of the white dwarf. Conservation of angular momentum leads to a disk. And there's a loss of some material through viscosity that causes angular momentum to be, it's gained by some material which is then kicked out, and it's lost by some material which collapses down onto the white dwarf. In recent years, we realized that a few of these white dwarfs have strong magnetic fields. So I put a magnetic field in here. In fact, we don't think that that's essential to the nova phenomenon, but it may be in any event. So there's a magnetic field here, and that can disrupt the disk. In any event, this material does eventually make it onto the white dwarf. And he said that provides the hydrogen fuel that will degenerately explode. And so that essentially is the nova paradigm. And here it is in detail. I like this slide. I scanned it. I first drew it about 30 years ago when I gave a talk on novae, and it explains what I just told you. Okay, so here's a cartoon of what's happening here, and the essentials are explained here. Here's a white dwarf. Most of them carbon and oxygen, sort of 50-50 in the interior. Depending upon the mass of the white dwarf, you might have a very thin helium layer, 10 to the minus 4, 10 to the minus 5th solar masses. And you have in the accretion disk roughly solar material from the secondary star. Lots of hydrogen and helium. It's undergone some nucleosynthesis, so it could be enriched in some of your heavy elements. But basically, excuse me, we'll assume that it's solar. But certainly lots of hydrogen. Falling down the gravitational potential of the white dwarf, becoming degenerate, semi-degenerate, here when it hits the surface, and heated by the infall and by the pressure of subsequent overlying accretion layers. And so the temperature slowly builds up from this material, which has hydrogen, lowest Coulomb potential. And what happens is, after enough accretion has occurred, the temperature will reach a temperature in which proton capture can occur. Same process in massive stars, the CNO cycle. Basically, you have your carbon-12 and your nitrogen-14. With the addition of hydrogen at high temperatures, you have the proton capture reactions giving you this stuff. Okay? And it occurs explosively. And the key to it is this: the degenerate equation of state in which pressure is related only to density and not to temperature. And so if you have a temperature fluctuation that causes more energy, it increases the energy generation, drives up the temperature, but there's no adiabatic expansion now because the equation of state is not the perfect gas law. And so you have this runaway, basically, where instantly, in a matter of a second, the temperature will shoot up because of increasing energy generation, higher temperature, until the Fermi temperature is released, which for a 1 solar mass white dwarf is around 10 to the 8th degrees. That then releases the degeneracy and it stops the interaction. The energy generated in that process is sufficient to eject all the secreted matter out into space. And that's the nova outburst. So the key is the white dwarf, which gives you degenerate conditions, the secondary star, which provides the hydrogen, and on the white dwarf, left long ago, and you have the explosive phenomenon. And in musical terms, repeat and fade. That is, it repeats. After this happens, you get accretion again after a period of time. The mass loss causes the secondary star to move slightly further away. That cuts off the accretion. Evolution of the secondary star causes it to expand. Accretion starts once again, and you get a recurrent nova phenomenon. That we're not sure of. According to we don't know. But we believe from the models that the accretion disk, by and large, it depends on the mass of the accretion disk. And the transit time in the accretion disk is much less than the time it takes in between these outbursts. And so the ejected mass is much greater than the accretion disk, which causes us to think that the accretion disk is blown out also. But there's some uncertainty because that's a theoretical result. That's the accretion. So that's the current paradigm. And here are some models. So it's been modeled by 4 groups. Starfield in Arizona, Namoto in Japan, Priamic and Kovets in Tel Aviv, and Hillebrandt and Thielemann in Garching. And they all get the same result, pretty much. And they model this. And they have all found that the important parameters in describing this are the mass of the white dwarf, obvious, sets the depth of the potential well, and the rate in which you get accretion. Less accretion, longer recurrence time. But basically, you'll get an outburst, and depending upon the accretion rate, and here are accretion rates for the models, 10 to the minus 13th solar masses per year up to 10 to the minus 7th. And you can see that basically your temperature profile in terms of time in years, and I'm not sure if you can read this, here's 10 to the 9th here, is essentially the same. That is, the temperature stays down around 10 to the 7th. Actually, it's lower than that. They have that as the initial condition. And that's lower than your proton capture reactions will occur. And so the accretion steadily drives up the temperature until suddenly proton capture occurs, and it drives up the temperature to the Fermi temperature, and then degeneracy is released. And it's all over. And you can see that you almost always reach the Fermi temperature. You're going to get energy generation until you reach that. And the time it takes to do this depends on the accretion rate. And so for rapid accretion, it can happen in 100 years. For very low accretion rates, 100 million years. Also, the luminosities that you get from this process generally always end up at the Eddington luminosity. They start low, and then you can see basically as soon as the nuclear reactions occur, and this really isn't a matter of seconds, you get a luminosity that is roughly the Eddington luminosity, so radiation. Excuse me? Oh, less 30? Yeah, T-Pix, recurrent nova. 25, 30 years. Yeah. So it is believed that all novae are recurrent. 20 years? 20 million years. Here, there have been multi-cycles. People have followed this cycle after cycle, and you can see, they start with it, and they do the hydrodynamics. This is the Tel Aviv group, so that's Shara and all. And again, you can't see this, but basically, here's the luminosity. In solar luminosities, this is 10 to the 4th, Eddington luminosity for one solar mass star. And you can see that here it's every 3 times 10 to the 5th years. For these parameters, this is a half solar, 2/3 solar mass white dwarf, accretion rate 10 to the minus 9 solar mass. Boom, 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 boom. And here the maximum temperature, 10 to the 8.2 or 3. The Fermi temperature is it keeps recurring. Looks good. And generally, they find also in their models there's a certain amount of mixing. Let's see how many slides ago is that. The heavy element enrichment that we measure in our nebular analyses, we believe comes not from this material. Some of it may be from evolution of the secondary star. Most of it, we believe, is caused by a mixing here in the interface between the accreted material and the surface of the white dwarf that drags up carbon and oxygen. And that then is redistributed by these nuclear reactions, and that's what we're measuring when this stuff is ejected. So, that's the NOVA model. Here are the results, actually. So this ends the middle part of the talk. And here are some models by the Tel Aviv group. Again, let me read them for you. Here's a model of lower mass white dwarf, 2/3. And here 1.25. Here are different accretion rates. And I highlight this result here, which is a realistic model. 1.2 solar mass white dwarf below the Chandra-Zaccar limit. Accretion rate 10 to the minus 9. You can see here for this model, here's the amount that was accreted to produce the outburst. Here's the amount that is ejected. Notice that this is greater than that by a small amount. That is, one of the interesting results of NOVA models is you generally eject, because of the energy that's produced, more than you accrete. And therefore, the secular change in the white dwarf mass is it decreases, not increases. And this is very important for trying to explain type 1 supernova. Can you have collapse by arriving at the Chandra-Zaccar limit from accretion onto a white dwarf? And most of the modelers say no, you don't. You don't gain mass, you lose mass. And so you don't get supernova this way. I'll show you why I think this result may need to be changed. Although, notice that for different accretion rates, you can enter a regime up here if you accrete at a higher rate, 10 to the minus 7. Then the models actually show that you can accrete slightly more than you eject. So that result, secular decrease in the white dwarfs, is dependent upon the accretion rate, according to the model. Usually you find from the models that there is production of helium, and therefore the helium is enhanced. And you can see here what you start with and what you end with. So there's an increase in the amount of helium, the fraction of helium in the ejecta. And here you do have an enhancement both at the beginning and the ejected heavy elements. But you can see it's Z is much higher than the solar value of 0.03. And here's the temperature maximum. So the point of all that is, that's, you know, if I were to stop the talk right here, you'd have a good explanation of the nova phenomenon, and most people would say that's what a nova is. So we go back and tell the Chinese everything's cool. A couple of years ago, since my history is in nebulae, I thought it would be interesting to try to determine the kinematics of nova. Okay, so most novae, all this occurs in very small angular size. And so we can't really tell what's happening. So for something that is not spatially resolved, best way to understand it is spectroscopy. So spectroscopy here, I'm a spectroscopist. Recruiting for spectroscopy. I thought it'd be nice to look at high spectral resolution at novae to try to determine kinematical structure, and maybe that would tell us something. So with Massimo and with Alessandro and with Elena Mason, we got time at Lucia on their very nice shell spectrographs, fiber-fed ferros. Novae are bright, small telescope, 1.5 meter. For 3 years, we had a nova survey, and we published some papers. In fact, I think your thesis, was your thesis on, Nova Sag, 2004. So Alessandro wrote a thesis on that as part of this consortium. Here's what spectral evolution of most novae is like. Time is going up. Here's 4 spectra. This is a nova I just picked, Serpentis, 2005. 1 week, 1 month, 3.5 months, half a year after the outburst. And all nova spectra look like this, really, basically. They start off looking with a P Cygni profile, having very broad profiles, very high velocity gas. They evolve over a period of a few months from this P Cygni, which consists of low ionization material, basically, iron 2, sodium 1, to a higher ionization emission spectrum that's similar to planetary nebulae and H2 regions. Here you see the evolution from iron 2, P Cygni, means an optically thick expanding gas, to an emission spectrum with broad lines, oxygen 3507 and nitrogen, you know, the typical nebular line. So that's what we're looking at. And I had studied these things for years at moderate resolution because I wasn't interested in anything except an abundance analysis, and you don't need to resolve the spectral lines. You only need the flux. So here we were trying to do the kinematics, and this is what surprised me. First of all, let me say that the interpretation of that spectrum is a fairly standard, obvious one. You start off, here now time is going down, you start off with this situation where the white dwarf explodes, send this material off. It is optically thick, and therefore that produces this P Cygni profile, which produces an expanding photosphere until the expansion drives down the optical depth, and then the photosphere, the moving photosphere, actually starts migrating back to the white dwarf. And at this point, you have all of this material that now is optically thin and radiates emission spectrum. And so this explains that basic evolution. So for years, people have thought, yeah, well, this is how you understand that. So far, so good. This is what surprised me, at least, and which I ignored for several years, not analyzing this data because I was not interested in the absorption lines. I was interested in the emission lines. In fact, it was one weekend when I finally saw so many absorption lines, I thought, geez, people are going to ask me about these, and I should have an answer. In fact, the absorption lines, not the emission lines, I believe, hold the key to understanding the nova outburst. And so I changed myself into an analyst of absorption lines, not just emission. Here is a close-up of that same nova, Serpentis, in the sodium D region, 5,900 angstroms. Okay, so here, 2 weeks after outburst, you get this big P Cygni profile here, characteristic of 2,000 kilometers a second expansion, which is roughly the escape velocity from a white dwarf, and that's what you expect. It is punctuated by sharp sodium D absorption. And what's nice about sodium D is the fact that it's a doublet. And so when you see stuff like this, you can make a certain identification because, in fact, the spacing of sodium D is 5.95 angstroms. The spacing of these features is 5.95 angstroms, and it has the right ratio in the sense that the F value of 5890, is twice that of 5896. So these are sodium D features, having an expansion velocity less than this big P Cygni profile, which is optically thick. Remember that. So you've got the nova ejecta, 2,000 kilometers a second. Superimposed on that, you have these features. By the way, this is the interstellar medium. You always see the interstellar medium, sodium D, and calcium 2K. So, 2,000 kilometers a second, but superimposed are several distinct kinematical components having sometimes a very low internal velocity dispersion. So this stuff is kicking out at 800 kilometers a second. That has a velocity dispersion of only 35 kilometers a second. So something has thrown this stuff out at 1,000 kilometers a second, and it remains cold. This is sodium D. Sodium has a ionization potential of 5 volts. You know, you sneeze on it and it's ionized. So this is amazing. 1,000 kilometers a second, still neutral. Low internal velocity. And they're multiple. So what's happening? Well, whatever it is, it's happening everywhere. Here are 4 objects. Okay, a week after outburst, basically. Here's 2 weeks. All the same in our survey. They all look like this. We have 15 objects. 12 of them show this, and the 3 that don't only show that because either the instrument wasn't available or it was cloudy and we couldn't get to them. They all show same feature, very broad P Cygni with lower velocity, smaller internal velocity dispersion components here. Here you see the narrow sodium D, not so narrow here. Okay, here's the same object I was showing you, Serpentis 2005, with the multiple one. Here's an LMC nova, and here's Sagittarius. Sodium D, all right? And each one of them also has this broad absorption P Cygni in it. All at 2,000 to 3,000 kilometers a second. All of these narrow objects, which are between you and this expanding material, all have lower velocity. Another interesting feature, if you look at the evolution of the spectrum, time now going up, 1 day, 2 days, 1 week, 3 weeks after the outburst, you see that the velocities change and the material is accelerated. You start off here in this object at 2,000 kilometers a second, and after a period of days, you end up at 2,500. So this material, which is whipping out, is speeding up. Same is true of these sodium D features. Starts off at 850, ends up at 1,100. They all show that. Sorry, they don't all show that. There are a few where there's not much acceleration. But there are clearly distinct components here. So this is what we're trying to interpret. What's going on? You know, we expected this stuff. We expected the big P Cygni. What's this? Well, it's this, I think. This is the simplest interpretation. The black, I hand drew this one weekend. I'm analytic, not digital. Es decir, soy viejo. The black is the nova ejecta. So here's the secondary, here's the white dwarf, okay. Kablam, sends out the black stuff, 2,000 to 3,000 kilometers a second. Out, and it's optically thick. Outside of this material, now in red, is this overlying material that has low ionization with lower velocity. And it's going out typically 700, 800, 900 kilometers a second. But must be overtaken eventually by this material. But we don't know what the distance is. In fact, when I first started showing these spectra to people a year or so ago, they all said, no, it's probably just interstellar material. I should say, not so. Not only are both of these accelerated, but they both disappear in 2 months. Something happens that causes this absorption to go away in 2 months. Well, if that's true, it can't be interstellar. The interstellar stuff just stays forever. So it's got to be nearby. And also because it's accelerated, it has to be nearby. For an Eddington luminosity, it has to be within 30 astronomical units. So that's pretty close. Another thing, I was going to say this, about the acceleration. What is it that can accelerate this material and yet keep it very low ionization? Okay, two things that can produce acceleration, radiation or particles. If you throw particles at something, you almost always have to have that momentum converted into energy. It's very difficult to communicate with particles, only momentum and not energy. So if it were particles, it would heat the material. Particles are out. It's got to be radiation. So I think that radiation is doing it. And that's not a surprise, because if we go way back, I should have called your I'm going the wrong way. I should have called your attention to this. If you'll notice in the nuclear reactions here, you get all these P-gamma reactions, and then after you have the proton-rich material, because it's away from the valley of stability, it stabilizes. You produce positrons. The positrons react with the electrons and annihilate, and they give you 511 keV gamma rays. So it has been predicted that gamma rays should be produced by the nova outburst. Lots of gamma rays, both from the proton capture reactions and from here. They've never been observed yet. And it's starting to be a problem. It's like the solar neutrino problem. That's why I gave the analogy. Where are the gamma rays that are supposed to be here? It is a real puzzle, particularly with SWIFT being up there. Let's see, let me go back the other way. And I don't have an answer from that other than to think that there must be enough material either here or here to absorb them all. It takes a column density of 10 to the 25th. Or so because that's the Compton scattering cross-section, to absorb all the gamma rays. And that's a very high column density. And we should have detected some with SWIFT by now. We have not. In any event, so we're trying to understand now. All this stuff sits out there. Okay, this is new. And basically what I'm going to say is this is a very important part of the nova phenomenon, I believe, because of the following. So we tried to understand what is this stuff? You know, where did it come from? So, spectra. It turns out that when you look at the other parts of the spectra of all these nova, and you try to identify, so there are all these other lines that I'd never seen before. Even I've taken hundreds of nova spectra at moderate resolution. Never noticed until high resolution. I'm a convert to high resolution spectroscopy now. This stuff had always been there, and so don't take low resolution spectra if the size of your telescope and the instrument enables you to take high resolution. Things will occur that you did not think would happen, and this happened to me. And even after I saw these things, I was not interested in them. Basically, they had to clutter up the spectrum so badly that I figured, hey, I've got to understand this stuff. So we did the identifications. And they're really interesting. Here you see them. Okay, so we've got those multiple sodium D-sharp features. We apply that radial velocity. We look at the spectrum, and we go to the multiplet tables. Actually, now there's a much better way of doing it. You do it online. You use Peter Van Hoof's V2.05 line list, electronic, 10 to the 6 transitions. Any spectroscopist has to have this as a major resource if you're trying to do line identification. So we've done this. And here's what you see. You see all of these S-process elements and iron peak elements. Strontium, chromium, yttrium, titanium, vanadium, barium, and the like. And there they are. So there's this material out there that's beyond the photosphere. It's in a dilute radiation field, and we don't know where it is. So we apply a simple interstellar medium type analysis to it using the equivalent widths to determine column densities. And so this is very crude, very uncertain, best we can do. Here actually is the best spectrum. I realize you can't see this, but look at in LMC 2005, there's hundreds of these lines, sharp lines. They're all scandium, vanadium, chromium, titanium, strontium, yttrium, and barium. Didn't come from the white dwarf. Got to come from the secondary star. In any event, so we've measured the column densities here. You know, we wrote a paper that appeared about a year ago in APJ. Oh, the interesting thing is, if you look at the Grotrian diagrams of all of those lines that I just showed you, they all come from singly ionized iron peak or S process elements, and they don't come from the ground state. They come from excited levels. And that means that this material has to have temperature. So it's sitting way out there, and it has a temperature. You can get the excitation temperature by comparing the strengths of the lines from different excitation potentials. And then you can do a simple analysis, knowing the F values, and get column density. And here's the result. Again, you can't read this, but here are all the, scandium, iron, and the like. Here are the F values, many of them measured, some theoretical. Here's the excitation potentials in inverse centimeters. Here's our measured equivalent width, and here's the column density. Very simple one-line equation. The interstellar people do this all the time. The column densities are large. Iron, 10 to the 18. So if this is solar material, multiplied by 10 to the 5th, 10 to the 6th, the column density of this absorbent material is around 10 to the 23rd, 10 to the 24th. So that's pretty healthy column density. Relative abundances. Well, first of all, the temperatures are around 10 to the 4th, same as the nebula. So this material's way out there, and something's causing it to have this temperature. And the abundances do look like they're above solar by about an order of magnitude for the iron peak. Now, I think there's a lot of uncertainty here, so I'm not sure how much I believe this result. But there is an indication that this is evolved gas. And for the S process material, the strontium and barium, hard to say what the abundances are there. This is below solar, that's solar. But the interesting thing is, with those column densities, you can easily get the mass, because if you've got material out there with a certain column density, you simply multiply by 4 pi r squared, and that gives you the mass. So what's R? Well, we see it for a month. It's going at 1,000 kilometers a second. Distance is velocity times time. So that's your minimum radius. And we get that the material out there is of the order of 10 to the minus 4 solar masses. And that's a lot of stuff. More than the ejecta. So here's this stuff we've never known about. It looks like there's more of it out there than is thrown out by the nova. So that's the interesting news. Where did it come from? In our paper a couple years ago, I thought it was, well, because of the iron peak elements, I think it cannot come from the white dwarf. It's coming from the secondary star. And so in that paper, we speculated, it's pulsations or something. We don't know that is causing this star, the second, okay, here's a white dwarf. I'm going to talk about this in a second. Here's some hydrodynamic calculations done in Moscow by the Russian group, Saitov, Desicalo, Boyarchuk. I thought at that time, which I didn't know, I wasn't aware of a decade of work that these guys have done. And so what we did was we said, well, this secondary star must be throwing off material out there. And it's out there before the nova outburst. Mike Shara and Ken Nomoto in the past year have called my attention, at least, to the fact that that cannot be. The energy it takes to lift 10 to the minus 4 solar masses from the surface here out, basically to infinity is greater than the nova outburst. And so unless this thing's been doing this, and why should it do it? Because if it requires that much energy, it should produce something as bright as a nova. We don't see that. Didn't make sense. And so I've been puzzled. And Mike Shara, just a few months ago, called my attention to the fact that these Russians have been doing calculations for a decade, 3D hydro calculations, that indicate that, in fact, there is a bow shock that is created in the outer part of the accretion disk, produced by the motion of these binaries, which are going around in 5 hours. A lot of kinetic energy there. And what is happening is there's a certain amount of material that is thrown off from the outer accretion disk, produced by viscosity, that causes some material to migrate inward, others to go out. That creates a bow shock. That heats the outer part of the accretion disk and produces this common envelope. And they've been saying this for 10 years. I was unaware of it. And I can't vouch for the veracity of their calculations, but they've done a lot of them basically and indicate that there is this dense common envelope that exists around close binaries that are undergoing mass transfer. So I suspect that this may well be what's producing all of that material out there. So I think here is what is happening. You've got the black stuff, the nova, coming out, adiabatically expanding, comes out initially at a temperature of 10 to the 8th Kelvin, but within a matter of days from adiabatic expansion, cools down to 1,000 degrees. For those of you on the webcast, a plane is going over. This material here in red is being ejected hydrodynamically as per those calculations and forming a common envelope. So I think that's the source of this material that builds up to 10 to the minus 4 solar masses having a distance 3, 10, 25 AU. As the white dwarf starts heating up, before it undergoes the nuclear reactions, there's a period of time when its temperature is 10 to the 5th degrees before it becomes 10 to the 7th or 10 to the 8th. And it essentially photoionizes low level, this material out there, and is what produces this temperature of 10 to the 4th. Since this material is coming from the secondary star, which has evolved and may therefore have S-process material, that's what causes this to have enhanced abundances here. And so it sits out there fairly quiescently, just waiting for the nova to go off. And when it does, basically, you get this phenomenon. Eventually, the nova ejecta overtakes this material here out at 25 AU, and at the velocities of 2,000 kilometers a second. That takes anywhere from a few weeks to a few months. And that collision then is what causes the spectrum of the nova to convert from its absorption P Cygni spectrum to the emission spectrum. And the interesting thing is, it also explains the square box rectangular profiles of the emission lines. One of the first homework problems you have in a stellar atmosphere's radiative transfer course is, what is it that will produce a rectangular profile? And the answer is, if you have a thin spherical shell expanding, at a constant velocity, you get a square profile. And that is exactly what happens in this situation. You've got this material out there. This material comes into it and produces this interface where there's a forward and a reverse shock. The reverse shock does not radiate because the density is so low, because the material that's expanding out there is decreased to very low values. This material, which is sitting out there, has a density that is more like 10 to the 4th, 10 to the 5th, similar to nebular. And it is heated and it radiates, and that's what produces the emission lines. And this quasi-spherical geometry is what produces a square profile. Yes. There are several interesting things here that I believe this also explains. X-rays, gamma rays have not been observed, but X-rays have. But usually not at the time of outburst. And this has puzzled people. Suddenly the X-rays appear several months afterwards. People wondered why. That's why, I think. This is very similar to the Castor-McRae-Weaver interstellar bubble studies of more than 30 years ago. They explained around hot stars you have a wind, and it causes the sweeping out of ambient interstellar gas. And there's a lot of hydrodynamics that was done 30 years ago. A very similar situation. And so I think that's what's happening here. Now, let me end with this. The interesting thing is, here's 4 novae, early spectra where it's P Cygni, later where you have the emission lines. You get these squarish profiles. Note, this is helium-15876. This is sodium deabsorption. Note that the width of the emission line corresponds to the velocity of these sharp sodium features, not the broad ejecta velocity. I believe that is caused by the fact that this material out here is much more massive than this. And this material stops that material when it hits it. And we've been puzzled, all of us who study novae, why it is that the ejecta are always moving out at 3,000 kilometers a second. And years later, when you see the resolved shell, it's only moving at 400 kilometers a second. Why is that? I believe the reason is there's this stuff out there that we weren't aware of, and it essentially stops this. And everything then moves out at the velocity of this material, which is less than this because it's further out and therefore is not accelerated as great. So, conclusion, summary. Novae, the paradigm is basically correct. Novae are close binary systems. The high-resolution spectra show these two separate systems. The ejecta moving out very rapidly, this slower-moving stuff that we weren't aware of that's circumbinary. We believe that this stuff comes from the secondary star. It is enriched in your elements that come from an evolved star, the evolved secondary. I think the origin is the secondary star, but via the accretion disk, the outer accretion disk. So instead of having your mass transfer entirely through the L1 point, in fact, what immediately happens is a lot of that material does not end up in the white dwarf. Instead, it's kicked out here into this huge reservoir of material that surrounds the star. And then the colliding shells are very important in explaining things like dust formation and X-radiation. And finally, the last thing, which is very speculative, and so I'll simply say it for your consideration. Why is it that when we see nova, you always see this material out there? Is it a coincidence that it just happens to be out there when the nova goes off? Since it has much more mass out here than the material that is ejected, I believe that, in fact, the novae are produced not by mass transfer through the L1 point. I suspect that there is occasional collapse of this material from some change in viscosity that causes much of it to rain down on the white dwarf, and it produces the nova outburst and also gives you a mechanism for exceeding the Chandrasekhar limit. Perhaps, this is speculation, and is a way of putting white dwarfs over the Chandra mass limit. Might produce a type 1 supernova. So, well, I was going to say thank you. I want to say one other thing. I was here 15 years ago. It's a real pleasure to come back to this institute. But for you people, it's an honor to work here. I've always believed that what's important in life is not position, it's gradient. And of all the places I've been to internationally in the past few years, this institute has a steeper gradient in terms of its scientific productivity than any other place I've been at. So if it is true that it's gradient and not position, and I believe that, you people are in a very preferred position, and you should appreciate that. So good luck in producing great science with the GTC. Thanks.
Now we have some time for questions, so John?
Talking about gradients, what's the mechanism for the acceleration of the two different types of gas? The gas that goes from 2,500 to 3,000 and the gas that goes from 800 to 900. What's the mechanism that does that?
Short answer, I don't know. Longer answer, I suspect that there are some X-rays that are seen, not just sometimes shortly after outburst. Most of them usually occur within weeks after the outburst, and I think are produced by the collisional shell. I believe that there is downscattering, speculation, okay, of the gamma rays to X-rays by Compton scattering, and that produces those X-rays. And in fact, one of the characteristics of absorption of X-rays is you can get the transfer of momentum, and most of the energy goes to a few of the electrons that are ejected. And so I'm thinking, I haven't done the calculations, these should be done. I think that that may be what produces the acceleration. And the reason, of course, that the circumbinary material has a lower velocity and lower acceleration is because it's further out, and simply 1 over r squared causes its acceleration to be less. So it's easy to say that. That sort of makes sense, but it would be important to do the calculations. But that's the answer I would give.
Okay.
I have a question about symmetry. I assume this explosion has not spherical symmetry, but the ejecta seems to be...
Sort of. There's some interesting well, you can see there is a symmetry. There's a rough symmetry there. In the resolve shells that I showed, it looked like there was a certain amount of sphere. But there is clear spectroscopic evidence. One object in particular, Norma, 2005. You see the sodium D at about minus 800 in absorption, and you see sodium D, the same two features, plus the same velocity. So it's clear that some novae do have some jets. So there's spectroscopic evidence for that. And of course, we know that there are a few objects that are called polars, strong magnetic fields, 10 to the 8th Gauss. Nova, the famous Nova Sig 75 was one, where the rotation of the white dwarf is locked onto the rotation of the star. And it's easy to think that perhaps in a strong magnetic field you would have ejection like that, yeah.
Yeah, would you expect short-lived nuclei from your explosive nucleosynthesis? Short-lived nuclei. You have explosive nucleosynthesis, right?
The beta decay is short-lived, 10 minutes. Those beta decay, is that what you're asking?
No, heavy nuclear decay of isotopes, titanium, etc.
So I haven't done those calculations, and I'm not sure, but I think not. Because the Fermi temperature is 10 to the 8th, temperature always has to be below that. The only nuclear reactions that can occur are proton. A little bit of helium capture, alpha capture, a little bit, and that's what produces some of the high helium. Temperatures are too low to do anything with the heavies. So we think, and again, I'm not sure of this, you'd have to ask the nuclear people, but I believe that nothing greater than helium and hydrogen can undergo any fusion.
Okay. César?
Well, I suppose that the circumbinary gas is on the plane of the orbit, no? Yes.
Good question. I'm not sure. I suspect much of it is, but most, la mayoría, okay, of the gas. Podemos hablar en castellano, pero en público,
don't worry.
And so at a temperature that's low, you would expect most of it concentrated in the plane. But it has a temperature of 10 to the 4th. And so when I talk with the Moscow group, and I haven't done it yet, I'm going to try to find out what the density distribution is, because obviously you would expect higher column density in eclipsing systems. And I don't know if that's the case. I'm sorry, is that your question?
No, the point is that if the circumbinary gas is on the plane, then you will have different observational facts due to the orientation, no?
Right. And so we should look for that, and we don't know what the inclination is except for the eclipsing systems, and they usually don't start eclipsing. Again, you don't see through this material until some years after the outburst. And these stars, I don't know if they've been studied by people ever since our survey. And because we were using a small 1.5 meter, 2.2 meter telescope, we could only observe them at this resolution for 6 months. We stopped, and yeah, hey, if I had more telescope time, we should do that. Someone should do this. You people, you have access to telescopes. Someone looking for a thesis here. This is great stuff, and I'm interested enough that I would help participate. There's a lot of interesting observational studies. So anyone looking for a thesis, yeah, these objects should be followed, and things like that looked into.
Okay, I think we have time for a few more questions, comments.
Could it be that part of this second component, the one that is cold and outside, that it is... okay, the question is whether this second component...
the sharp absorption.
Well, the one with sharp absorbers,
yeah,
right?
Yeah.
Whether this could be leftovers of previous bursts rather than
Everyone asks that. Everyone asks that. So... I really doubt it. And the reason is that absorption always disappears in 2 months. So why does it disappear in 2 months? Yeah? Oh, no, you still see it. You see these years afterwards. It disappears while we are still looking at it in 2 months, and the nova is still bright. It disappears not because the source disappears behind it, it's because the column density of that ion disappears.
Maybe it just get heated up.
Exactly. It got heated up, which means it is near the nova. Is that what you're asking?
I'm not really aware of the scales and all these kind of things, so...
so you're trying to
make... It was a kind of
what
naive
point
question.
are you trying to make?
Whether, rather than being material that...
material left over.
Yeah.
Well, again, if the material is far away, you wouldn't expect it to be accelerated. So why would material from an outburst 10 to the 5th years, or even 100 years earlier, it would be too far. It would not be accelerated.
Well, the expansion is not uniform, so you expect that some parts just remain there for long, whereas others, I don't know.
Yeah, no, it could be. It could be. Hey, what?
There's a big mass discrepancy.
Well, it'd be a huge mass.
Wouldn't be enough mass.
It would, yeah, it would be, yeah. It would be hard to explain because of the column densities, which are measured. And you determine the mass of the material by multiplying by 4 pi r squared. You get a huge... No. It's interesting. You know, often in science, you know, someone asks a question like that, we say, no, can't be. And it turns out to be correct. So it's something that we probably should pay some attention to. Right? You know, right now I don't think that it's correct, but it might be. All I can do is give you my sense, my reason for currently rejecting that argument. But
a comment and a question. The comment is, I'm doing the old nova follow-up, so don't sell it too much around. No, older, because
high spectral resolution.
Now they have to find with 20th magnitude you can't.
You now have a big telescope. Yeah, but you don't have a but you do not have a high-resolution spectrograph. And for many years, I didn't support high-resolution spectrographs. I am a convert.
We'll talk about it over lunch.
I am a convert. Yeah, I believe every major telescope should have a high-resolution optical spectrograph. High in the infrared also. Yeah. Seriously. You know, all of this came about by accident because I was interested in the kinematics of the emission lines and really saw those absorption lines, didn't pay any attention. I thought, no, I have no interest in, you know, finally I thought, wow.
The question is, you mentioned that magnetic fields, they don't play a role.
We don't know that they play it. We don't know. Maybe they do.
Because there was a paper in the early 90s by Brian Warner where he was suggesting that most of the old nova systems were magnetic, if I don't remember bad. So I was wondering if there was any connection or what was your feeling about it?
I haven't haven't done the calculation, so I can't comment intelligently. There has been maybe that's generally the case. There's been a problem with the initiation of the nova reaction in some of the models, and it's been thought that perhaps concentrating the accretion in a smaller place would change the heating characteristics, and it would change some of the nova models. And I didn't think that people generally thought that was something that was generally important for the nova phenomenon, but I may be wrong. I don't recall that most of these nova modelers have advocated high magnetic fields. The Tel Aviv group, most of theirs are not using magnetic fields, and they get good agreement. But who knows?
Pollination. I mean, how do you explain this outburst that you get from the water? Yeah.
Where? Do you see it here? What? Here? This?
Yeah.
That's not really from the white dwarf. That's from the outer part of the accretion disk.
Well, okay. But
So it's through the L3 point. I don't know if I said it's through the L3 point. There is a minimum there, and so this stuff is, when it's hot and it's in the outer part of the accretion disk, it starts streaming through the L3 point. And so that's what gives it sort of this concentration.
Collimation.
Yeah, the collimation. L3.
Okay, we have time for one last question. If not, I think we should thank again Professor William.